Hi, I'm David. I go to Denver Jewish Day School. I will be a junior next year, and for my starter project, I decided to build a delay pedal for guitar. And what it does quite simply is it delays the signal, so I play, and it plays. There are three controls. There's delay time, level, and repeats. Delay time controls how long it takes, so here's the shortest. It just sounds the same because it's playing at the exact same time. Here's a little bit. It's like a slap back. And all the way up in short mode goes like this. It also has a long mode, which basically quadruples the time that it can do because it sends it through three more circuits. So here's the maximum delay time it can possibly have. Which is quite a bit. I can also decide how loud it is with the level knob, which is very quiet. A little louder, and I can even take it out of the signal completely. You can't even hear it. The repeats also decide how much of the signal gets fed back into the circuit and gets delayed again. But because of that, the signal gets a little bit degraded, and because of that, it's what makes it analog and allows it so that when the infinite repeats, you get a sound like this. Fades into noise. But it can do something very cool like this. Dubstep type sounds. Also works in the long mode, but it glitches out a little bit, makes it sound a little cooler. And just click it off with the foot switch, and it's true bypass, which means that the signal gets fed all the way back through. Okay, so as you can see here, this is the schematic of how the delay works. First of all, this is the input signal. It says it's stereo, but there are actually only two lugs, so it's not actually stereo. One is hot, one is ground. As you can see, it just goes through this circuit right here. These circuits right here are acting as a gate to this signal. And as you can see, it's just moving through this. You'll see that there's delay out. So this is the latter half of the signal. We're not going to focus on that for now. First off, we just have this signal right here, which just basically acts as a noise gate and a rectifier for the signal. It prepares it and goes with that transistor for when you actually are going to go into the delay signal. And that's how part of the switching works. As you can see down here, where it says delay in, that's the continuation from the signal up from above. Right here is the clock circuit. The delay time, as you see, is controlled by a control voltage in the potentiometer, which is 1 megohm right there. The chip is right there that goes to all the other chips and tells them to clock as well. So as you can see here, there's a set of 5 clock chips right here, as I explained earlier, and I showed you in the oscilloscope how that works. Those are all driving these actual delay chips, which are 4,096 steps each, and they each carry on the signal and then pass it on to the next one. And because of that, you get A, signal degradation, but B, the more important part, delay. As you can see here, it just goes through that. You can see that there's a short and long switch, and because of that short and long switch and the balance, basically when you have it in short mode, there's a switch right here that's engaged, and that basically just takes the first delay chip and bypasses all the others. If you have it in long mode, it actually goes, rather than through one, through all 4. And so that essentially quadruples the delay time you can get. However, you do lose more signal degradation because it's going through more steps and delayed more often, or for a longer time. After that, it goes to the delay out, as you see right there. And so that comes back into the original signal where it gets rectified and goes through a series of gates again. As you can see, these transistors right here are to keep it from letting in too much noise, and they're controlled appropriately with that. In addition, you have the same op-amp IC, and that basically just repeats it, or that links it back in. As you can see, the repeats potentiometer will decide how much to send back through the signal, and in addition, the delay level attenuates how much you actually get. And what you have here is basically a final gating of it, and then finally an output mix. As you can see, there's also a switch right there. And there's a switch right there, and that's basically to ensure true bypass, so that when it's in the off position, you're not getting any delay signal at all. It's just following A, going up that line, and all the way back down to the output without any processing whatsoever. So that allows for true bypass connection. Okay, so here's the actual circuit work. As you can see, there are a bunch of ICs. This right there is the op-amp. It's what makes the signal loud enough to actually be dealt with. This right there is a noise filtering chip. This was the IC that I originally thought was extra, but it actually helps to cut down on the background noise of the clock signals. These 5 chips right there are all clock generators, and they are dual phase, so they have 2 output of clock pulses. And between the 5 of those, they power these 4 actual delay chips, and these are the ones that have 4,096 steps in each of them. So between 16,000 or between about 16,000 steps, the signal gets degraded quite a bit. But that's the analog sound that you get, and it also makes it sound a little bit warmer and a little bit cleaner. All these trim pots do various different things. Some of them bias how much signal the delay actually gets, and because of that, if you turn it up even a little bit too high, it gets really, really gainy, and it's not exactly a good signal. But also, if you turn it down too low, you can't hear it. There's a very minimal range where it'll actually work. There's a delay time trimmer. You can make this delay go pretty loud if you want to, or pretty long if you want to, but that also makes the signal quality degrade a little bit more. So the shorter you get, the shorter delay you get, but the more clear it is. You have noise canceling trim pots right here, and you use a signal tester to test certain pins on these delay ICs. You also have a balance knob, which is basically controls the balance between the short and long modes. Your feedback trimmer, which also controls how your feedback delay is. I set mine to do the dubstep, as you saw earlier. As you see, there are various different capacitors. Some of them are holding charge for the circuits, and some of them are filtering the noise and filtering out DC for some places. I have both aluminum electrolytic and ceramic capacitors, ceramic discs, and film capacitors. There are various resistors throughout the circuit to ensure that the current and voltage are matching appropriately. And there are a couple of transistors that seem to be acting as noise gates and only open up when sufficient voltage is applied to the gate in the middle of it. And with all of that, it's able to filter the noise to give you a nice sounding delay. In the input, you have just a standard guitar in. Right there is the 9-volt DC input. I haven't quite figured out how many milliamps this draws yet, but that'll be another thing that I might look into. This is the mixed output that gives you your dry signal mixed with your delay signal, and that's controlled by the level knob on the front. And then here's the dry out, which is basically just a straight connection from this to this, and you just get your original guitar signal without any delay mixed in. And here's the little switching down there that decides to make a true bypass. It's a 3PDT, meaning that when you press it, 3 poles are switched to the other position, and that turns on an LED, puts the circuit into the circuit board, and when it's not engaged, it just connects the input straight to the output through a trace in the circuit board. So here I've hooked the delay pedal up to an oscilloscope, grounding to the casing. Here's remnants of a test that I was doing before, and I'm basically I set the trigger level to trigger properly because I'm going to be testing the clock first. I'm using channel 1 currently because that's what the trigger is set to identify with. I have my time division set at 50 microseconds, and that's also in order so that I can see this square wave that these clock chips are producing. I have it set to AC coupling so that it won't, because it's very offset due to the increased voltage due to the op amp in the circuit and just how everything is operating at a higher voltage than neutral, or than zero rather. And because of that, I just need to have the offset gotten rid of because it's really the oscillation that matters, not the actual voltage amount. So right here, it's currently paused. I'm going to touch one of the outputs of one of the clock chips, and you'll see that there's a square wave and that's the clock pulsing. And so it's very, very, very fast, but you can see as I turn the delay time, I can actually control it. So delay time is at its maximum right now. You see that the period's decently long. As I turn the delay time down and I'm probing the same point, the period gets closer and closer together. And so because of that, that tells the delay chips to operate at an even faster rate, and because of that faster rate of operation, it delivers the delay much faster as opposed to later. And due to that, you get a longer and shorter delay, and that's all controlled by this knob. So what I've done now is I've set up the delay with a bunch of probes. As you can see here, I'm using a function generator. It's set to 200 hertz, which is somewhere around a G note, but not quite, because it's impossible to tune this to an exact note. I'm taking an output to that, and I'm hooking it up right here to this DP-DT switch, and I'm going to be using that to send it into the signal. I've got the ground hooked up to the other lead so that the signal won't buzz while it's not on and give me noise, and so because of that, that'll be my way to send signal into the system. I'm using channel 1 as my trigger channel, and that's just hooked up to the input, so you can see the original. Here's a remnant of the test that I was doing before. You can see the original signal, and then I'll quickly ground it, and then you'll see the repeats of that on channel 2. You notice from this, though, that the channel 2 repeats have a very much higher amplitude, even though they're set to the same scale. The reason for that is because there's an op amp in there, and so because of that, it raises the volume of it to make it the pedal able to deal with that. So I've set this in this single mode right now, which means that it'll do one run in 1 second increments on all of these marks, and you'll be able to see that as soon as it triggers the input, you'll be able to see an input signal, and then you'll be able to see the output of the delay channel, which I've hooked into the delay circuit right there specifically. It's not the mixed output, it's really the delay. And you'll be able to see each individual repeat until it eventually just fades into noise. So here it is set to long mode with a couple repeats in the system, not infinite, and you'll be able to see the results from it. And you heard that in the amp as well. So you see that these are just getting quieter and quieter to the point where you can't hear them. But each one of those was a repeat, and as you see, it just faded into noise. What I'm going to do now is I'm going to lengthen the delay time so that you can see a much longer delay. And I'm going to turn the repeats down so that it doesn't feedback so much. Alright, I'm going to set it up again, turn the amp volume up a little bit. And as you can see, each one is a little bit longer than before, and decayed after it looks like 1, 2, 3, 4, 5, 6 clear repeats before it just fades. So what you have here is, you saw in the previous video, I turned it down, up the repeats to infinite, and I turned down the delay time, and I got kind of a dubstep kind of sound. And so I'm going to do that again right here. Use the amp so you can hear it. And here it is with just like one input. So here it's delaying. And now we're going to turn up the repeats.
Oh, did you already have this?
Just going to take the signal, keep bringing it through. And you can see as I turn down the delay time, the period will decrease because that the frequency is going to go up. Get a little bit more signal to trigger the thing again, and you can see it right there. So the period is going down, pitch is increasing. And there you go. And now, you see that there's just what appears to be just a blue line. Really what that is a bunch of sound waves. And as you can see, as I turned it up, they got much closer together. Because of that raised the pitch of the sound and made it audibly a higher pitch. And before, you could see, and there it is, the higher pitch. And before,
maybe bring the,
there you go. And before that, then you can see how far away through it.
Yeah, and
So now what I've done is I've moved the probe from just taking the delay signal and I'm having it take the mixed signal. So I'm going to show you how the level attenuation will actually get rid of the delay as you start to mix it out. So I'm going to start with full delay time, a few repeats on the signal, short delay time, and full level. And that's what that looks like. So as you can see, you had overlap. So right there, you had the original signal, and as you can see, it's at a lower amplitude because it's not straight out of the delay signal, it's being mixed back in. So that original signal is actually the original signal, just with the delay. These are the delays because, as you can see, the original signal is gone, and it's a little bit less clear to see, and that's because it's not hooked straight into the delay channel. So I'm just going to zoom in a little bit so you can see a little bit clearer. There you go. So now what I'm going to do is I'm going to do the same test, but I'm going to down the level of the delay about halfway. And you'll see that this amplitude right there is going to get smaller. As you can see, much, much, much smaller. I'm going to turn it down even more. Even smaller. And now I'm going to turn it all the way up, and you're going to see, basically, you're just going to see the original signal, and then just noise from there on out, because no delay will be there and no original signal will be there. It'll all be grounded. And with that kind of variation, the trigger has been set a little bit higher, like that, for example. And if we're synced to channel 2, which it isn't, then you wouldn't have seen all that noise there, because at that point the delay is mixed completely out of the signal except for in minute amounts.